Hello everybody. So today I will talk about the system design of Tinder and I will do some deep dives today. So today's topics are I will talk about first three low latency of stack loading and then strong consistency of matches and then number three is scalability. So that being said, I get started with the first one. So low latency of stack loading. So I will talk about this part, stack generation daily job. So I actually handled this part yesterday. So this stack generation daily job reads the user and then finds the stack of profiles which matches his preference, maybe 30 users, and then create the stack profile record in the database. So I introduced the daily job so that it can take as much time as possible because it has overnight. But even, I mean, I'd like to be more clear on this part. So when I take a look at this, the biggest thing I have to be careful is about the geolocation searches. So let's say there is a user and he, specifies the maximum distance 10 miles. This stack generation daily job has to find the users who are inside of that radius. So that's something I have to take care. And so what I can do here is I can use so PostgreSQL actually has the geolocation searches. So firstly, what I do is store this latitude, longitude data in the points type. So this is a type. But points type now, with this point type, I can do the search with the, boundary of the plane. I mean 2D plane. But this points, type doesn't consider the curve of the earth. So if I'd like to include, I mean, if I'd like to take the curve of the earth into the consideration, I have to use PostGIS extension. So with this PostGIS extension, now what I can do is I create the index of geolocation index with this point type. So with this, now I can use the index built in the PostgreSQL, and this stack generation daily job can find the users quickly. And yeah. So the good thing of this approach is that I can include the query with the geolocation, and also query with other attributes. And what it does is, PostgreSQL does the query optimization, including the searches with this attribute using B-tree index, and the search with the, this, location with the geolocation index. So PostgreSQL can combine these searches, queries internally, and does the query optimization. So that's the best point of this approach, I can say. Yeah. Okay. And of course, there's another solution that I use the, for example, Elasticsearch, and I, use the CDC, change data capture, and export the, consumes the data changes, and Elasticsearch should have the, those data. And in the same way, I can use the Elasticsearch's geolocation index and also other, B plus 3 indexes. So the same thing can be done with the Elasticsearch. Okay. So that about the geolocation search. And maybe I'd like to add something I was, I misunderstood yesterday. So actually, I talked about the concern that the location update from the user may overload this database. So maybe I was thinking that maybe I should separate the data for the, you know, um, profile and preference with separate them with location data. But on the second thought, this is not a big concern in the Tinder app. So let's say I'm developing the Uber. In Uber, driver's location should be very accurate, and it has to be, updated every 10 seconds or maybe every 1 minute, probably every 10 seconds. But in the case of Tinder, it doesn't have to be so accurate. Let's say user just go to the convenience store near his house. Actually, the location doesn't have to be updated. So I can say if the user moves more than 1 mile or maybe 0.5 miles, the location has to be updated. So the frontend can use the adaptive location update and the conditions that the frontend has to send the update rated location is very infrequent. Yeah. So that being said, I don't have so much concern on putting this latitude longitude data onto this user profile data. Yeah. Rather, I'd like to take the advantage of the query optimization of the PostgreSQL. Now I will talk about the second topic, which is strong consistency on matches. So probably this is the most interesting topic in these deep dives. So I will talk about this part. So when there is a user, let's say user 2 already swiped user 1, and user 1 now already swipes user 2. And I want the strong consistency here. So why do I need the strong consistency? I will make it more clear. So let's say user 1 up swipes user 2 and user 2 swipes user 1. So this is the ordinary, normal, occurrence of the event. So let's say user 1 swipes first, then user 1 process. Firstly, user 1's process writes the swipe data, and then it checks the match record. And this is not much. Sorry. User 1 process checks the opposite swipe. This means swipe from 2 to 1. And it's not found, so no match. And then let's say user 2 swipes user 1, and user 2 process checks the opposite match, user 1 to 2, and it's found in swipe table, and match is created. So this is the ordinary flow. But let's say user 1 and user 2 swipes almost at the same time. In that case, it could happen in this order. So user 1 swipes user 2, and wait a minute. So user 2 swipes user 1, and record is created. So so user one. Okay, so now I understand the problem here. So yeah, actually I stopped the video and looked at my note. So the problem here is, as I said here, this creating the swipe and creating the match record, these two operations has to be done in the single transaction. Otherwise, it is possible that swipe is created but match is not created. That kind of inconsistency problem. So when I set the transaction here, and let's in PostgreSQL with the default isolation level, read what was it? So PostgreSQL's isolation default level is read committed. This means that the data is visible to other transactions after that transaction is done. So let's think of this. So user one now starts the transaction here and creates the swipe record. And user 2 starts the transaction here and creates the user 2 to user 1 swipe record. But here, because user 2's transaction is not finished yet, sorry, it's here. So this swipe record is not visible yet to the user 1's process. So it assumes that there is no match yet. And here, when user 2's process does this user 1 transaction is closed. If it closed, okay, but let's say user 1's transaction is not closed yet, not committed yet. In that case, it is possible that user 2 cannot see user 1 swipe record and detect it as the no match. And finish the transaction. So this is the fundamental problem of this approach. Okay, so I will tell you the solution. So the first solution is actually give up strong consistency. Or I should say, use reconciliation job. So, okay, here I told that I would use the strong consistency for matching, but let's forget this non-function requirement. So, possible approach here is we don't create the match in the same transaction. We don't have to. But instead, I try to make the swipe record and make this match find as the best effort. Yeah. So it means that, let's say there is a so oh wait, let me fix this. So sorry, I still say I will do this in the same transaction, but let me continue my explanation. So let's say I accept this problem to occur, and instead, let's say in an hourly basis, I create the hourly reconciliation job, cron job. So I would call it match reconciliation hourly job. And this job checks the database, swipe table, and also match table. And if there is a missing match because of this issue, so if this average job finds it, it creates the match record. So in this way, what happens is that user, both of the users who match together, who match each other, are notified with push notification. Either of them are notified in UI immediately, but both of them are notified with push notification. But I think this is totally fine, actually, because this occurs quite rare when both of two users swipe at the same time. And yeah, basically, we don't take care too much if which swiped first, yeah, as the user. So I think this approach does work. Okay, and okay, now we come back to here. And if I do this, I actually don't have to make two of them in the same transaction. Yeah, this match creation to be, best effort. So in this way, even if the swipe, fails, even if the creation of the match fails, so for some reason, the swipe record is created, so later match is created. Yeah. So in this way, we can accept the, temporary data inconsistency. But still, this problem occurs because even though the query to create the swipe is, the query creates only the swipe record, it still does the transaction. So in PostgreSQL, even for creating one record with create statement, it actually does the transaction internally. So it means that still this problem can occur. Yeah. So that being said, yeah, this is the first approach. Okay, so maybe I was wrong. Wait, so I said even if I separate creating swipe query and creating match query, still the race condition can occur. But now I'm thinking that it occurs if this swipe DB has a read replicas. If this is a single node, only the primary database, primary node, what happens is there is one process which creates a record and commit, and there is another process which creates a record and commit. So user one and user two. So the later one, which finished the transaction, swipe creation transaction, so which created the swipe later can definitely see the match created by the first user. So if this PostgreSQL is a single node, this race condition doesn't occur. But let's say I use the read replica of PostgreSQL. In that case, let's say the latter user reads the data from the read replica, and there is a rare lag between the first user creates a swipe record and it is propagated to the read replica. In that case, the latter user may overlook the swipe by the first user. So in that case, the data race condition occurs and match is not created. So yeah, but as I said, in this approach, I have some match reconciliation already job, so we can accept it. Okay, so I added something more, but this is the first approach. Okay, so now I will be more, compliant with the non-functional requirement here, strong consistency. So I don't use the reconciliation already job anymore. So the second solution is make use of the PostgreSQL's ACID property. And actually, I have three sub-solutions here. So number one is using the isolation level. So what I mean to say is, the problem here is the transactions are interleaved to each other. But if I use this PostgreSQL isolation level serializable, this doesn't occur. So PostgreSQL handles the transaction serializably. Yeah. So the actions in the same transaction are done in the before other transactions are done. Actually, this is different from linearizable. So what I can say with serializable is, after looking back, I can reason the order of the transaction as if each of them occurred one by one. So this is the serializable level of isolation. So with this doesn't occur. But the problem is, what happens internally in PostgreSQL is the queries which is run to the PostgreSQL, even if it is a read query, which doesn't have nothing to do with this, they are all waiting in the kind of queue to be handled. So this isolation level serializable is very bad in terms of the performance. So I actually don't want to use this. And the second approach is using the pessimistic rock. And I would say pessimistic row rock. So pessimistic row rock is this means that I use a select for update. So the first user kind of locks the match record. So wait a minute. So what I can do is, yeah, so I make sure that I use the row rock on this match record. So if there is a user who'd like to update this match record at the same time, they have to wait in the queue. But this queue is per row record. So let's say user runs does the transaction and creates a swipe record. It's okay. And then use the select for query to get the match. And then if he can find it, he tries to update it. So, but these updates occur in the, sorry, wait a minute. I'm a bit confused. Okay, so I thought of this a little bit, and now I'm thinking of deleting this swipe record. So the approach I talked, pessimistic row log. So this is the approach which, which strictly gives the order to the update and read of the specific one record. And the problem here is, if I create the swipe record, user one's process has to take a look at user two's swipe record. So, I mean, user one to user two swipe record and user two to user one record, swipe record, are separate, different, which means that I can't use the row lock. So instead of this, what I'm thinking is, so think of this swipe as the dual swipe. So, and when I think of this as a dual swipe, I don't need this swipe record, actually. So, I mean, I create the swipe record, it's okay. Oh, wait. Okay, so let's say I named it dual swipe record, and this I create this to user ID 1 and this to user ID 2. So user ID 1 should be less than user ID 2. I set that, definition here. And now I put user 1 likes user 2. So this should be true or false or none. No. And I also create user 2 likes user 1 and swipe out. So of course I need user 1 swiped out and user 2 swiped out. So I changed the database table schema here to use the row lock. So in this way, what happens is that user 1, if he tries to swipe the user 2, it reads this dual swipe record with user ID 1, user ID 2 is 2. And it uses select for update query. So this means that that process reads from the primary DB and keeps the lock, takes the lock. So until that transaction is done, other process, user 2's process cannot read this dual swipe record. Instead, it has to wait in the queue, waiting queue. So with this, what happens is that user 1 firstly takes the lock of this, then updates the user ID 1, swiped out, and user 1 likes user 2 to be true. Then user 1's process finish the transaction. And now user 2's process can work on this work on the transaction. So it tries to select update this record, and now user 2's process takes the lock. And because user 1's transaction is already done, user 1 swiped out and user 1 likes user 2 is updated already. So now user 2 update this and this, and then that process can know that there is a match, and it creates the match record. And user 2 is notified with the UI match notification, match UI, and user 1 is notified with the push notification. So yeah, that's how I can use the row lock. So I created the dual swipe record here, and yeah, that's it. But I actually have one more thing to be clear. Who creates this dual swipe record? So I can say the first user has to create it. But it is also possible that those two users create the same record twice. So I put the unique constraint on user ID 1, user ID 2. So in this way, user 1 firstly tries to create the record because he comes first. And then user 2 also tries to create this dual swipe record, but it fails. So in that case, okay, actually I searched a little bit on the internet, and yeah, okay, so I put the unique constraint here, and now what happens is that user 1, any user, just try to create the dual swipe record just in case. So I can use this query. So insert into matches. So user 1, ID 1, user ID 2. Yeah, and this and this, and on conflict do nothing. So if there is a conflict, it doesn't do anything. And if there is a, I mean, if the record doesn't exist yet, it creates a record. So firstly, each client, each process does this query to make sure that the dual swipe record is created. And now it continues to, it does what I explained right now. Transaction, starts the transaction and do select for update with row rock. So yeah, this is the pro. So let me quickly explain again. So each of the process, user 1 and user 2, let's say user 1 is swiped user 2 and user 2 swipes user 1 at almost the same time. In that case, firstly, the process tries to create the dual swipe record, empty record with this insert into onConflict query. So in this way, the first record is definitely created here with empty state. And then the process starts the transaction. And in that transaction, it firstly use select for update query to fetch this dual swipe record and check if the opposite swipe exists already. And in either way, sorry, maybe I should say, firstly update the dual swipe record and then check if there is a match, and if there is a match, then it creates the match record and then finish the transaction. Because in each transaction, what it firstly does is use the select for update to get the log of this dual swipe record. If there is another process, transaction, which is locking this record, that process, the other process cannot start the transaction. So definitely this works. Okay, so now we'll talk about the another option, optimistic row rock. So this is quite simple. Yeah. So actually I use the same idea and I put some version key. So with this version key, when there is a process who tries to update the version, this dual swipe, firstly it reads the latest version, let's say version key is 3, and then it makes a query to update the attribute and also version key to be 4, which is 3 plus 1. And let's say there is another process who's trying to do the same thing. That process should query with the version key, which is just read. And so let's say there are two processes, and both of them reads version key 3 and version key 3 of the same record. And now both of them makes a query which specifies ID is something, version key is 3, and update these attributes. So both of them tries to update the query, throws the query with that version key specification. So either of them fails because version key is updated by the first earlier one. So the failed process reads the key again, reads the dual swipe record again with the latest version key, and then retries the update with that version key plus 1. Yeah. With where version key is 4. So this is the optimistic row rock. And yeah, this is good because in most cases, there isn't, I should say, a correlation. Yeah. But I think in this case, I'd like to use the pessimistic row rock because firstly, The biggest drawback of the pessimistic row rock is actually the waiting time of the queue. And the drawback of optimistic row rock is the client has to retry. So because there are up to one user, one process which is waiting for the same recode, actually waiting queue is totally fine. Retry is fine, but I have no concern of the waiting time in the waiting queue of the database of the row. So I would go with the pessimistic row rock. And of course, we don't have to create the version key column, which exists only for the transaction. I mean, to avoid the race condition. So I will go with the pessimistic row rock here. Okay, so this is, yeah, so the conclusion is I use the pessimistic row rock here. So with that, I can guarantee that the DIR swipe is, created. And there's no, overwork of the matches, even without the reconciliation job. Okay, so now we talk about the scalability. So scalable to 20 million data active users. So I do the quick back of the envelope estimation. And when I talk about the scalability, I have two perspectives. So one is the throughput, and the other is the data storage. So let's say it is scalable to 20 million daily active users. So let's say on average, each user makes 10 swipes. So I will, okay. So for the throughput, I will definitely talk about the swipe update. Yeah. And because I'm pretty sure this is the most heavy loading for the server. As I said before, location update, this seems also heavy, but let's say how much user moves a lot in a day. So okay, maybe each user moves maybe 10 miles a day. In that case, the client has to update the location 10 times a day for each user. So it's almost the same as the swipe count. Yeah. So I'm pretty sure swipe is heavier. Yeah. So I calculate the swipe throughput. So 20 million data active user, 10 swipes. So there should be 20 million swipes per day. And because one day is 10 to 5 seconds, so this should be 2K requests per sec. So 2000 requests per sec. So this is actually not so big. It's correct. 10 to the 5. Yeah. 20 million. Okay. So this is 2K requests per sec, write request. This can be handled with single PostgreSQL database. I mean, where is it? Here, SwipeDB. Yeah, because typically PostgreSQL can handle 10K requests per sec of writes. Yeah, if the query is not so heavy. So I think, yeah, I don't need the sharding for this. Okay, good. And now, that being said, for DB layer, it is fine. And for server layer, actually this isn't a big issue because we can use the horizontal scaling because each request is stateless. So it doesn't matter which server handles the request. For each of these services, it does the auto scaling, maybe with EC2 auto scaling according to the CPU usage or memory usage or amount of the traffic. Yeah. And SwipeDB is fine, and StackDB. So I'm also pretty sure this is fine. Yeah. And for ProfileDB, as I said, the write request from location is quite pretty, infrequent for each user. So this shouldn't be so heavy. Yeah. But of course, this is too heavy. I can do the sharding. So it's fine. Yeah. Okay. And of course, if the database, yeah, okay, yeah, sorry. For stack generation daily job, I can do the sharding, or I should say partitioning. So as long as each user, I mean, so let's say, yeah, I can kind of make this daily job, and I mean, I can use the job orchestration. So let's track the progress of the per user stack creation progress, and if it's too slow, we can increase the number of daily job servers, worker servers, and we can speed up the speed of the create progress of the stack generation. Okay, so this is about the throughput, and I will talk about the storage size. To be honest, the biggest concern is dual swipe, because user table, I'm almost pretty sure for 220 million users, I can store them in a single PostgreSQL like AWS Aurora, because nowadays Aurora can store 512 terabytes or something. Let me just quickly check. So let's say there are 100 million users in total, and let's say each user has 100 byte, maybe 1 kilobyte of data. In that case, 100 megabyte, 100 kilobytes. Yeah. So the data size, the total data size is only this. Yeah. Okay. Kilo, mega, giga, 100 gigabyte. Yeah. So it's totally fine. And for stack profile, I can say for each user, 30 recommendation, or maybe with some buffer, 50 recommended records are created. So it should be 1000 gigabyte, which is 1 terabyte. Again, this is fine with AWS Aurora. Yeah. And of course, stack profile is deleted every night, so it doesn't go beyond 1 terabyte. So it's fine. Yeah. Okay. And actually, my concern is dual swipe recode. Oh, yeah. Maybe what I can do here is, because, okay, yeah, it's okay. Yeah, just a quick idea. I thought of including the ID or height or something like that as the cache of the, I mean, I do the redundancy of the data between user record and stack profile. So in this way, client doesn't have to fetch the user's record, but I actually don't do that because user record can be fetched only once when user started swiping. Yeah, so it only once a day and it fetches only 100 records. So probably it's not heavy loading. I mean, it doesn't, I mean, redundancy here in stack profile record doesn't have so much benefit. Okay. Now I will talk about dual swipe and match record. So dual swipe can be quite heavy because this is n squared. So let's say there are 20 million daily active users. So let's say there, or simply saying, because there are 100 million users at max, probably this doesn't occur, but there should be 100 million times 100 million. But yeah, this is not realistic. Sorry. So let's say each user makes in total before the deletion of the query, sorry, profile, he makes 1000 swipes. In that case, the total swipe by the user is 1000 times 100 million users. So this should be 10 billion swipes. So because two swipes are in, okay, so let's say these swipes are, doesn't include any mutual swipe because I'd like to know the upper bound. So in that case, 10 billion records are created, and let's say each record has 100 byte. So in that case, giga. So this should be, wait a minute, 10 to the 10 times 11 byte. So kilo, mega, giga. Wait, is this correct? Wait, am I correct with this? 100 million users and 1000 swipes is million billion, maybe 100 billion swipes. So this should be 10 to the 13. No. 10 to the 10. This is 9, 11. And because I have two tens, this should be 13. So this should be 10 terabyte. Yeah. So okay, actually this is 5 terabyte. Yeah, and this makes sense now because yeah. Okay, yeah. Or I should say, for each user, it creates 1 kilobyte of record. But when I create 100 byte of record, which is 0.1 kilobyte, and each user makes 1000 swipes, so it should be 100 times of this. So yeah, this is correct, 10 terabyte. Okay, so even for dual swipe record, it can be stored in the um, single PostgreSQL in terms of the data size, and of course in terms of the yeah um, wait throughput too. Sorry, no. Ah, yeah, true. So zero swipe. This is loaded with 2K requests per sec, and the data size should be 10 terabyte of storage. So it totally fine with single primary node. And of course, I can do the read replicas for three read throughput increases, and also for the kind of availability. Yeah, because if the primary node is down, the read replica can be promoted to the primary database. Yeah, or something like that. And also for stack there, yeah, I talked about this already. Okay, so now I talked about all of them. Good. And the thing is, when user deactivates his account or her account, in case of the swipe, their swipe records can be deleted. Much records can be deleted asynchronously. So in that way, actually, the data doesn't have to keep increasing. Yeah, so that's another point. We don't have to take care of the storage size too much. Okay. And maybe I want to quickly talk about one more case. So what if user updates the profile preference or profile, his profile itself or location is updated. In that case, it's possible that the you know the stack profile data is outdated. So last night, the stack generation daily job showed that some user, let's say user B is meets the preference of user A, but now next day, because user A updates the profile or maybe user B updates the profile or location, it's not suitable or maybe it can happen. To avoid this, what I can do is in the client side, it does the final check if that user still meets this condition. And also what I can do is this stack generation daily job should create the stack profile with some buffer. So let's say we should show 30 users. In that case, this generation daily job create maybe 40 recommendation kind of stack profile records. And in that way, if the client then notices that many of the users are skipped because of the changes, maybe this client can call one more API call to fetch additional maybe 20 or maybe 10 or 20 stack profiles. So that's what I can do. So this stack generation data job does create with buffer, and from then does the final safety check. Sorry, final validation as the final check. Okay. Or maybe if I'd like to handle this problem only in the backend, we can do kind of change data capture. We can use the change data capture of this user table, and there should be a worker which kind of invalidates the stack profile created already. So let's say so this is CDC is consumed by this invalidator, and it checks the stock profile. Yeah, and invalidated. And if it notifies that the stock profile is now very, less than the required number, even with buffer, it triggers stack generation daily job to, create the stack profiles again. Okay, good. Now, yeah, I finished my today's system design practice. Yeah, I talked a lot, I think. Probably I will talk about the geolocation index tomorrow, or maybe the day after tomorrow. Yeah. But that being said, I finished my today's system design practice. Thank you so much. Bye.